this question on a concentration cell. So let's remind ourselves, what's a concentration cell? It's a voltaic cell hooked up between two of the same half cells, but that they have different starting concentrations of the ion. So in this case, we're working with a tin 2 plus half cell. And in one side, we have a high concentration, 4 molar, that's on the right side. And in the left side, we have a 0.05 molar concentration. Okay, so my guiding principle for any of these concentration cells is to always ask yourself what needs to happen to make the concentrations the same. If you start there and work your way through that process, you will get the right answer. So I'm gonna draw this out. This is something that I also find is helpful to do visually. Okay. No one is writing home about my drawing skills. That's fine. They get by. So on the left side, our SN2 plus is 0.05 molar. And on the right side, it's 4.0 molar. Okay, and this is like any other voltaic cell setup. I'm going to have a salt bridge, okay, that is connecting, that's allowing flow of cations and anions. And then I'm going to connect my two tin electrodes with a wire, which allows for the flow of electrons. So electrons will flow up in this wire. We've got a salt bridge here. So there's some some medium that has NaO3 in there, some salts that can easily migrate. So they're movable and can charge balance for us. Because without that, this voltaic cell doesn't move. We can't just keep packing in negative charges on one side. Okay, so we know that our reaction, one of them is going to be doing this, the reduction. And one of them is going to be doing the opposite, the oxidation. Okay, so this is our reduction. And so that would be where our cathode is, how we would name the cathode. This would be our oxidation. This is how we would name the anode. Okay, so we look at these two and we say on the left side, I have the smaller concentration. To reach equilibrium, okay, to lower, to get to the place where the system wants to be, I need to raise the concentration of 0.05. tin 2 plus on the left side, and I should lower the concentration of tin 2 plus on the right side. So they're going to meet somewhere in the middle, right around 2 molar. Okay, that's what's going to happen. So then I ask myself, which one of these reactions increases the concentration of tin 2 plus? That is my oxidation reaction. So to get there, I'm going to have tin go from tin solid to tin 2 plus. That's going to generate tin 2 plus on the left side, bringing up the concentration. Okay, so this I now can identify as the cell where oxidation happens, and then therefore as the anode. And I know that by definition, electrons always flow from the anode over to the cathode. So over here, let's just double check that this makes sense. I want my tin 2 plus concentration to go down. So I'm going to give it electrons to convert it to tin solid. So that also works. That makes sense that we should have a reduction reaction happening over here. And that this is our cathode. Okay. So the left side is we've already done on, so the anode. Okay. The constant, we haven't answered this question yet. We'll get there. That's a quantitative question. The concentration of tin 2 plus in the right cell is decreasing. Okay. I could also, if we want to just finish out some of this, I would say that my cations in the salt bridge are going to the right, they're going towards our cathode, and the anions are going to the left cell because those are negatively charged and we're losing those electrons. So that's going to charge balance for us. So to calculate E, so notice that there's no dot there, this non-standard cell potential, we're going to use the Nernst equation. Okay, so for any concentration cell, E dot is 0, right? Because our standard reduction potential is the same since they are for the same reaction. Okay, so it would just be 1 minus 1. Okay, that's 0. But we generate a voltage here because our concentrations are different. And so Q is going to be a number that then generates some voltage for us. N is the number of electrons transferred. So 2 is what we're working with here, 2 electrons. Okay. And then Q will be, I'm always going to have you define it as the concentration of the dilute side divided by the concentration of the concentrated side. Okay, this will ensure that you get a number less than 1, and the log of a number less than 1 is negative. And so we take the negative out of a negative, which would give us a positive, which tells us that we've written about this as the spontaneous process, right? Because this needs to be positive for it to be a spontaneous process. So you'll have 0.05 divided by 4. That's your Q value. So I get, when I punch all of this in, I have that our non-standard cell potential for this concentration cell is 0.056 volts. Okay, so it's a small number, but it's not 0. So that's what we'd be looking for here.